Hello and welcome everyone for coming to our section. I'm Dominic from Wilson, Holt and Associated Limited. In this section, I'm going to present the suppression of corrugation growth by rail damper. Here's the content I'm going to cover today. We'll first start with a brief background in rail corrugation. So what is corrugation? It is a wave-like rail that will form on the surface rail. Corrugation is clearly seen in photos, although it's only around 5 micron in depth. It appears more on the curved track, as though as a more complex wheel-rail interaction. And according to our experience, it typically appears on the low rail only. In general, short-pitch corrugation noise is a common cause of complaint from passengers. Regarding the corrugation control, rail grinding is a common practice to reprofile the rail surface. This process will however reduce the life of the rail. Each grinding typically grind away 0.2 to 0.8 mm thick of material off the rail head. Around 10 mm to 15 mm thick of material could be removed before the rail has to be replaced. Corrugation formation are usually tied to the wheel rail dynamics. One notch width is the stick slip model. The noise frequency is determined by the corrugation wavelength and the train speed. We believe that the corrugation generation mechanism is dominated by the rail dynamics. Our previous paper, published in 2012, showed that the two-mast rail damper could reduce corrugation growth rate by 41 to 47%. The rail damper alternating the rail dynamics was believed to be the reason behind it. To dig further into this topic, we conduct another side trial with our newly designed rail damper. Our rail damper is adapting the two-mast damping mechanism with a targeted frequency below 1 kHz. The vibration energy of the rail is transferred to the oscillator and dissipated by the resilient layer. The amplified vibration at the tuning frequency achieves high energy dissipation. It can dissipate both the vertical and lateral rail vibration. And you can observe that the oscillator has a much higher vibrating amplitude than that of the rail. Our first side trial was conducted in 2010 and lasted for 2 years. The results were published in 2012, and since then we have conducted a few more side trials, mainly in Hong Kong as well as other cities over the world. This is a rail damper that has been installed at the latest site trial in 2020 in Hong Kong. Next, we'll talk about the information regarding the test site and the rail damper configuration. It was a curved track with a radius of 300 meters. The track was supported by a resin base plate with a stiffness around 50 kN per millimeter. Corrugation was clearly visible on the photo there, although the depth is only around 5 micron. The rail dampers were installed for 200 meters long. And before installing the damper, our team conducted a track mobility measurement, the constant track. The measurement was conducted for the vertical and lateral mobility, where a accelerometer was placed on the rail head, between the sleeper and above the sleeper. Here we have frequency on the x-axis and mobility on the y-axis. The red line is showing the mobility between the sleeper, and the green line is showing the one above the sleeper. The result shows that the pin-pin resonance occurs at 1030 Hz for the vertical direction, while 570 Hz for the lateral direction. The lateral pin-pin resonance has a much higher mobility than that of the vertical pin-pin resonance. So the damper installed were tuned to 550 Hz with a damping coverage of 400 to 700 Hz. Damper were installed at each spacing between the sleeper at the low rail, while for the high rail, damper were installed at each fourth spacing between sleeper. Here shows some more detailed photo of damper installed. Our damper have a reference line to monitor the oscillator movement, and here's a full installation photo and also the installation process. The coming slide will talk about the measurement conducted and the result. We are going to present two measurements today, the rail corrugation roughness by the corrugation analysis trolley, and also the track decay measurement with 17 channels of accelerometer and 1 channel of impact hammer. First, let's look into track decay measurement result. Again, it's x-axis, we've got frequency in 1/3 octave band. And in y-axis, we've got a TDR in dB per meter. The TDR at our target frequency of 500 Hz band is improved by 3.4 dB per meter for the vertical direction, and 3.1 dB per meter for the lateral direction. With the damper known to be able to alternate the rail dynamics, next we're going to talk about the corrugation measurement result. We have conducted corrugation measurement within a field grinding cycle to monitor the corrugation growth. And please note that there is no damper installed in the first two grinding cycles, while the third one are the one with damper installed. Here's a graph that was presented in the paper. We'll then look into the roughness of each grinding cycle in the coming slide. With 1/3 octave corrugation wavelength band and its relative frequency, the train running speed on the x-axis, and the RMS roughness on the y-axis. As shown in this graph, rail corrugation have peaked at 31.5 mm and 50 mm wavelength band. A very interesting observation is that the peak at the 31.5 mm is very close to the peak-pin resonance frequency. And actually, in a 1/24 octave analysis presented in the paper, the peak was at 563 Hz, which is even closer. And let's detailedly look into the data. Among the first grinding cycle without any damper installed, we can see the corrugation at 31.5 mm has grown sharply. And again, in the second grinding cycle, also without any damper installed, different to the last grinding cycle, on top of the 31.5 mm wavelength band peak, there's also a 50 mm wavelength band peak there. After the rail damper has been installed for the third grinding cycle, you can see the corrugation growth has been significantly reduced. The two peaks are no longer that prominent. We also plot the RMS roughness of each 1/3 octave band against time. Here's the 31.5 mm band plot. The corrugation growth rate in the first grinding cycle is 1.26 micron per month. And in the second cycle, the growth rate was around 1 micron per month. And interestingly, after the damper was installed at the third grinding cycle, the growth rate is reduced to 0.12 micron per month, which is around 90% reduction. Among other short pitch corrugation wavelength band, around 54 to 90% reduction were achieved. So in conclusion, corrugation growth rate is reduced by 90% at target frequency, and the TDR was improved by 3 dB per meter at targeting frequency as well. So thank you for joining us today.